Hey folks, I just wanted to give you a bit of a tutorial on how to use the exoplanets.org website, and then we can go over to the exoplanet database, which is the one maintained by Caltech and IPAC to see what you can come up with. Really, all for this assignment, all I'm asking you to do is come up with one plot, two variables that you can use to really ideally support some of the contentions that we're dealing with. I mean, we're looking for trends. We're looking for connections between planetary variables that go beyond just our solar system. So here we're looking at exoplanets. And of course, exoplanets, if you look here at the methodology, they have a nice description of what an exoplanet is. So if you're really curious about that, you can go and read this. Anyway, so we're interested in the data, of course. So the first thing to do is just go play around, honestly. So if you click on plots here, it'll take you to a page where you can then input a couple of variables and create plots. You see it starts off with nothing. You got your y-axis and your x-axis, and they're just sort of there. You notice that if I scroll around, you can see in the upper left-hand corner my x and y coordinates. So that's kind of useful. It'll tell you it's already giving you a source or location. So when you create your graph and you want to export it, this will already be there. So you can then just create a citation in your page, and also gives you a date of access. So to create this, I would just go with a scatter plot, unless you really have something where a histogram would be applicable. For most of you guys, for most of these variables, a scatter plot is perfect. So if we look at what's available for the x coordinates, you'll notice there's a whole lot of stuff here as I scroll down through here, and it looks really complicated. And frankly, if I wasn't doing this tutorial, you'd probably say, I don't even know where to start. You know what? That's okay. So what I'm going to try to help you do here is go through a few of these and point out the ones I think you should really try to focus on. So in terms of these categories, there's, of course, planet information, stellar parameters, and these are all planets outside of our solar system. These are around other stars. So some of them are in astronomical catalogs, like the Henry Draper catalog, or the Bright Star catalog, or the Hipparchus catalog, which is actually named after the Greek astronomer Hipparchus, and so on. And if it's part of a binary system, it'll have a flag for that. The right ascension and declination the latitude and longitude in the night sky. So if you want to find the planets in the sky, this is what you would use. But it's not very good in terms of looking at actual characteristics of a solar system. These two characteristics aren't going to be useful to you. And then how it was discovered. Was it discovered through one of these four methods? So you can, it's either a true or false. Then there's stellar parameters, which are, what kind of star is it? B minus V is simply a color, a visual color index, essentially. So you could classify the star based on its B minus V value. It's blue minus violet, blue minus visual magnitudes. And of course, the same with these. Now, we do get down to, these are all catalogs, essentially, but here we get down to the distance to the star. This is the distance to the planetary system from us here in our solar system. So, unless you're looking at how that solar system fits into the larger context of our galaxy, these other variables are probably not going to be terribly useful to you. Now, then we get down to orbital parameters. And this is where things get a little more interesting. So you have the orbital period, which is how long it takes to get around the planet. Orbital eccentricity, how much of an oval shape or circular shape to oval shape is the planetary orbit. Zero eccentricity is a circle. There is no such thing as a circular orbit, but 1 is about as elliptical as it gets. So there's the argument of periastron. I wouldn't worry too much about that one. The time is now orbital inclination is kind of interesting. That's, of course, as we know, that most of our planets orbit in the plane of the solar system, but there is sometimes orbital inclination. Like the moon's orbit is inclined to the Earth about 5 degrees, and that's why we get lunar eclipses or solar eclipses only occasionally, rather than every time we have a full or a new moon. So inclination can be important, but it may not be terribly important in terms of actual characteristics of the solar system, but I'll leave that up to you. You could look at it. It does give you the inclination of the orbit, I would imagine, in degrees. The semi-major axis is, of course, that's a characteristic of any ellipse, going back to the eccentricity, right? A planet's orbit is either circular to elliptical, and it's always elliptical in some form. The semi-major axis is essentially how we define the average distance to the planet, but really it's the length of the semi-major axis of an ellipse. So you might have to go back to your geometry and algebra 2 classes to think about what that was again. But think of it as the distance to its star. That's honestly close enough. The planet's mass could be an interesting thing to look at. Separation between the star and the planet, again, that's just simply another measure similar to semi-major axis. Now, the rest of these are not necessarily terribly useful. So I would then go on to, transit parameters. And these are parameters that are determined as the planet has transited across the star. And you can look at a number of things, but the only ones that really get interesting here are planetary radius. That's essentially how big the planet is from the center to the outer edge. Also, the planetary density. They can determine the density of the planet. Now, that might tell you whether it's the terrestrial planet or a gas giant. You guys were harkening back to the lab, if you recall that particular characteristic. And surface gravity, which, of course, is dependent upon the mass of the planet. So if you were to graph mass versus gravity, you should see a relationship. If we keep on going here, you can look at a number of other variables that are here, but most of these are not going to be very useful to you. Stellar properties, again, the mass of the star. Maybe it'd be interesting to look at the mass of the star versus the mass of planets and see if there's a trend. Do more massive stars produce more massive planets? That's an interesting question. And of course, radius, density, and effective temperature of the star. These 4 variables might be very useful to you. But the rest of these here probably won't be. So I would say these 4 variables might be useful. A couple of these here might be useful, particularly radius and the density and gravity. And then some of these orbital parameters you might find interesting. So what I'm going to do is just create a graph. And to do that, I'm going to go and pick an x and y coordinate. Here I'm looking at the x. So I'm thinking about going down to my orbital parameters, or actually maybe my transit parameters. I want to look at this question of the, well, for instance, I know that density equals mass over volume. So there should be a relationship between all 3 of those variables that I should be able to pick up. So if I look at planetary radius on the x-axis, which will give me an idea of volume, and then I also look at the planet's mass, I should see some relationship. And indeed, although it's a bit of a messy relationship, you can see where it picks up planets of 0 radius have 0 mass. Of course, that makes sense. Can't have mass if you don't exist. So anyway, as you move up along here, there is a general upward trend here, although there's quite a bit of variability through here. Now, if we compare radius to, say, density, which is again one of those transit parameters, so we're going to go down here to planetary density. Let's see what we get. There, it's not as obvious a relationship. So where we have density over here in grams per cubic centimeters, of course, none of the planets in the solar system are much over 3 or 5 grams per cubic centimeter. So here, as we move along here and the planetary radius increases, we do then tend to get less and less dense. So while it doesn't look initially when you're zoomed out like there's a trend, as you zoom in, you can start to see trends that pick up. There are outliers. I would call those outliers. But as we get closer to closer to a Jupiter radius, we do get some more outliers here. We do kind of hover down around a planetary density very close to 0, but although there is quite a bit of variety. So here, for instance, this is about the density of the Earth right here, 5. There are planets that are the size of Jupiter that are more dense than the Earth. So this is kind of interesting because, in our solar system, we think of the inner planets as being small and dense, and the outer planets as being very large and not so dense. But it's not always the case that those 2 variables go together that well. So this is a situation where you have to ask yourself, if I'm going to argue that planets that are more dense, terrestrial planets, that with a density of around 5 grams per cubic centimeter, are generally smaller, much less than the size of Jupiter, than planets that are less dense. And that's my hypothesis based on our solar system. then obviously I'm looking now at a variety of other solar systems where that relationship doesn't hold true. So I can't draw a generalization about that. And then I would discuss that in my paper and leave it at that. I'm not looking for a, something you're going to publish here. I'm just looking for you to include a graph and then go from there. Now, let's say I wanted to include this. Well, I could copy the image. If I copy the image and then let's say I open up a document in my Google Drive and give me a minute for it to load. And I just want to create a new document. So I'll go here and la-di-da. Once it'll open, I will create a Google Doc here. And then I should be able to just paste it into that document. I might want to hit enter a couple of times. And I can do Control V. And we get nothing. Okay. So maybe you want to do is export this way. Yeah, it's going to export it as plot.png. There we go. There it is down there. Now, if I open that up, it'll open up a file or a program where I can look at the PNG file, Windows Photo Viewer, and I'll bring that over so you can see it. And indeed, there it is. So then I can just import that into my document. So it doesn't work to copy and paste straight from Exoplanet Data Explorer. We tried that, didn't work. So we have to go and click once you get it where you want it, and this is not a good place to have this particular graph, but once you get it where you want it, then you want to click export and go from there. You can only do so much. You can configure the axes a little bit, create a minimum and a maximum. And maybe for this, I might want to have a minimum of, on the y-axis rather, a minimum of 0, because obviously if we're looking at planetary density, you don't have densities less than 0. So, and I might make this no greater than 7. And if I do that, I've got a whole lot, I'm using my graph a whole lot more effectively. But maybe I need densities a little higher than that. Maybe I'll go to 10. Oh, I've still got some way up here. So, just play around with it and decide how big a graph you want to make and how many data points you want to include to make your argument. And then export it and save it. And honestly, I would just use this. You could go use the NASA Exoplanet Data Archive, but it is a little more complicated. So I would go to exoplanets.org and just use this data. There's plenty of stuff to work with here. You should note that these are error bars, both X and Y values of error. So you can actually get rid of the error bars, and then you don't have to deal with those. Then for some reason it went ahead and changed that value for some other reason. But it is a little cleaner that way. But the error bars are somewhat useful. You can discuss the error as well and get into that. So, all right, again, so you're looking to create a graph, and then you want to discuss what your graph means, and discuss it discuss what it means, and then discuss how it either supports what you know of solar nebula theory, or doesn't support it. And just make an argument, conclude, and that's it. Don't go over 2 pages, okay? But do cite this website and any other resources you use in APA format. All right, hope you guys have a great week, and I'll see you in cyberspace. I will probably create a video tutorial for next week as well, since we won't be meeting in person. It'll be useful to have some of these videos. So, all right, until we meet again,